Alright, let's talk about the relationship between work and energy, otherwise known as the principle of work and energy. So I'm going to show you where we're headed. I'm going to go ahead and just write down a definition. We can say that work is equal to the change in kinetic energy. And y'all have seen kinetic energy before. It's 1/2 times the mass times the speed squared. So the direction doesn't matter, we just need magnitude of the speed. Okay, so we are dealing with something with mass and something with a speed. If the mass is equal to 0, we can say the kinetic energy is equal to 0. And if the velocity is equal to 0, the speed, then we can say the kinetic energy is 0. So either case. Alright, now let's derive this. We have maybe some path where a particle goes from 1 to 2. Here's our particle in the meantime, and it's got some velocity that's tangent to the path. And if it's a curved path, it doesn't have to be, but if it's a curved path, then some force is driving this from 1 to 2, doing work. Then we can say that we are going to have, let me get a different color, a normal force and some component of a tangential force. And this all comes from the fact that we have some resultant force causing us to go around the corner and accelerate as we go around the corner in the tangent direction. So we also have an acceleration in the normal direction, a acceleration in the tangential direction. Now you'll start to see we're not really dealing with accelerations much. We're going to use it to derive this problem. But our principles of work and energy and conservation of energy are typically going to deal with displacement, force, and velocity. Alright, so let's derive the principle of work and energy. Let's just look at the tangent direction. If I sum the forces in the tangent direction, I get mass times the acceleration in the tangent direction. We've done this before. But what is this? If we say v dv is equal to a ds and rearrange it, where this is the tangential component of acceleration, we get this. And let's make the substitution. Substituting gives me the summation of the forces in the tangential direction is equal to mass times v dv over ds. Alright, separating by putting ds over on this side, we get the summation of the forces ds, which we will integrate from S1 to S2. This is the definition of work. And on the right hand side we get mass times v dv, and we'll integrate from v1 to v2. Alright, almost there. We can call this the change in kinetic energy. That's also equal to the summation of the work from 1 to 2 from all forces acting on it. We just had a resultant force, which was could have been a combination of 100 forces if we wanted it to be. Integrating the right side gives us 1/2 mv final squared minus 1/2 mv initial squared. So we can say the change in kinetic energy is equal to work, or 1/2 mv final squared minus 1/2 mv initial squared. Sometimes we want to know how much work was done. we can do that just knowing the change in velocities. If that is also defined as the change in kinetic energy. So this should be noted always is positive. We never have a negative kinetic energy. No such thing. We square the speed. The mass is a positive quantity. And for any individual, kinetic energy cannot be negative. Our change in kinetic energy could be, though. Okay. Yep, that's it.